Let's talk about convolution and correlation, and beginning to talk about some of the fundamental methods of spatial filtering, some of the most fundamental methods of spatial filtering. Before starting with the method itself, let's recall the concept of an operator defined by a neighborhood or defined on a neighborhood. Remember that we had the moving center of the neighborhood from pixel to pixel throughout the image. Let me draw that again. Oops. Right, so I apply, this is a neighborhood that is moved along the image, and I apply some operation around the pixels, on the pixels around the center, and change the value of the center of the neighborhood given the result of this operation. Right, so the operator T uses the values of the pixels in the neighborhoods to yield an output value at its center. When we have the operator that's a moving, when the operator is a moving matrix, whereas I get a matrix here with some values, and I do some sort of operation with this matrix, considering the pixels around and change the pixels at the center. So when this is the case, when the operator is a moving matrix, this matrix is called a kernel. It's only that you're going to hear over and over again in computer vision, oh, the kernel this, kernel that. It's just a matrix operator. Nothing more and nothing less. Now, this kernel, also called a filter kernel, has coefficients, right? Coefficients are the values of the kernel. And we apply these coefficients on the pixel values under the kernel. Right? So what happens is that I'm going to get the value of the kernel, apply on the pixel value here, and then the value on this position, apply on that, the value on this position, apply on that. And what do I mean by applying? It could be any sort of operation. You could sum the pixels, you could multiply the pixels. And in the particular kind of correlation and convolution we're going to see in a minute, it's just a sub-method of this more general methods of spatial filtering in general. Okay, so convolution and correlation are just the sum of products. Sum of products is, so I get the value, the kernel coefficient at this position, multiply by the pixel value, so this one is representing this portion here, this pixel here, multiply that, multiply this by this, multiply this by this, and so on and so forth, and this by this, so the whole thing, and sum the values, multiply each one of them, and multiply them all together, and apply the result of this operation to the pixel at the center. So that's what a convolution and correlation, that's what they are, basically, right? Okay, so there is a difference. So how do I differentiate a correlation from a convolution? Let's see an example with a single vector, a unidimensional matrix. So this is the original matrix, this is the kernel, this is the kernel. It's just a vector, right? It's just a vector. Now, when I apply the sum of products with the kernel and the way it's given, it's called correlation. When I apply the sum of products with the kernel rotated 180 degrees, so this is this kernel but rotated 180 degrees. So here I have 1, 2, 4, 2, 8, whereas the kernel rotate will be 8, 2, 4, 2, 1. This is called convolution. That's the only difference. And we're going to see that this difference is quite important for mathematical reasons. But let's see on this example, the simple example, the results of the applications of convolution and correlation using this simple image, which has only one pixel that's non-null, and this simple kernel, two linear matrices, two vectors. Now, starting position, I always apply the operation on the pixel at the middle of the kernel. So I start the starting position, I align the middle with the origin, right? And what happens here? These values are not defined. So what we have to do is to do what we call padding. Padding is just filling up these non-defined values with some sort of values. The most basic way of padding is just the zero padding, right? Where I fill up these undefined values with zeros and keep up with the procedure, right? So that's zero padding. We're going to see some effects of padding in a few minutes. Let's see how correlation works. So now this is done. Multiply this by this, multiply this by this, multiply this by this, multiply this by this, and sum the result. What's the result? It is 0. 0. Now, in the final result, this results in 0. Right? Move one position. Move one position. Move this kernel one position in that direction so that the 8 is now aligned with the 1. And the middle position is here. That's where we are going to operate the correlation, the result of the correlation. Now multiply 1 by 0, multiply 2 by 0, multiply 4 by 0, multiply 2 by 0, all 0. Multiply 8 by 1, it's 8. Sum everything. The result is 8. This 8 then is the value of the correlation applied to this position. So it goes in this way, one step by step, until you reach the end of the image, padded image, I should say, right? So whereas the middle of the kernel is aligned with the last position of the original image. This is the end of the procedure. The correlation result is just that. What happened with the kernel? So you saw the first, in this case, the kernel was 1, 2, 4, 2, 8. Where the correlation result, well, it's an identity, right? But that's an identity in correlation. It's just 1. The sum of multiplication of that will give you the correlation result 0, 8, 2, 4, 2, 1, which the effect of that will be to rotate the kernel. Right? So now convolution is exactly the same process. Whereas the kernel is already rotated 180 degrees. You do the same thing. You have to consider padding. You do the sum of products, substituting all the resulting value at in the middle pixel, and the result of convolution is then, well, in this case was just the kernel, the original kernel, right? 1, 0, 1, 2, 4, 2, 8, 0, 0. So that's just an example. There are applications. The applications actually start to make sense once we begin to have more interesting kernels. So it's the kernel that's going to direct your application. It's not the convolution itself, but it's the kernel. It's the filter that you use. And depending on the filter, you have obviously a different resulting image. Now, yeah, in a bidimensional example, it's exactly the same thing. So you can do this yourself. So this You have this kernel here, you have this original image here. The correlation result is the kernel rotated 180 degrees, and the convolution result is the original kernel, right? Because the kernel is already rotated 180 degrees in this case. The simple example, that's you can understand that. Now let's see the effects of various kernels and various the effects of the convolution using a number of kernels. Bear with me for a sec. So we are at this website. It's a very nice website. I suggest you to play with it later on. Now this is an image, probably of the author, where you can see all the pixels here and the pixels intensities, and he highlighted here which pixel he's talking about, and he drew that in a squared pixels, so that it makes it very has educational purposes. Now if we apply a 3x3 kernel, this is the kernel, it's just a 3x3 matrix. It has a number of distinct filters. Let's apply blur. A blur is just a kernel where I apply the sum of products using these values. So you see these values are here, and I'm multiplying. Can you see that? You are multiplying every region of this original image and substituting with a pixel in the other image, right? So I'm applying convolution on that and substituting. This image is already padded, so you can see that there is a black frame here. So I'm applying the sum of products using this kernel and generating this pixel here on the other side. And this is done by moving this window all over the image, right? You can see what's the effect of a bottom sobel. We're gonna see all of these filters later on, but just for you to have an idea of how the kernel looks like and the effect it has on the image. So you see the left sobel. What happens with the left sobel? You sort of highlighted the left edges of the image, whereas the right sobel, where is the right sobel? Highlighted the right edges of the image. Outline, let's see the outline. Oh, look, that's a nice filter, right? It's a nice filter. And look how the how the kernel looks like. It's just a number 8 in the middle and a bunch of minus ones around it. So why is that? We're gonna see that in a couple of weeks, if not next week. Right, and you can play with it later. You can upload your own files and apply a number of filters on. Let's pick up the original image that that's the image. That's the New York Public Library. Now we apply just the identity filter. Let's blur this image a bit. Blur this image, applying this kernel here. We end up with well, you see, let's pick up the original one, identity. So very sharp edges. Once you blur, you have obviously a blurred image. Bottom sobel, you have the bottom edges. Left sobel, you get the left edges. And sharpen is a good one. So you have a sharper a version of the image, and you see that the filter, the kernel is very simple. You see that it's just 0, -1, 0, -1, 5, -1, 0, -1, 0. So why does it sharpen the image? Try to think. What's it doing in the image? Stop the video now and think about it. That's gonna help you in the next lecture. Okay, right, let's go back to the slides then. Now, why do we apply convolution all the time and not correlation if they are basically the same operation? The reason is that convolution has nice mathematical properties. A convolution operator is commutative, meaning that if I apply one convolution f in one convolution g, I can apply g in f, so they are commutative. It's associative, so I can apply the convolution of g convolved with h is the same as the convolution of f and g convolved with h. And it's also distributive. The convolution of g plus h, where g and h are two convolutional operators, is the same as the convolution of f and g plus the convolution of f and h. Whereas correlation is non-commutative. Convolution is non-commutative. Correlation is non-commutative. Correlation is non-associative. Correlation is just distributive. So, given these very nice mathematical properties of convolution, it wins on the race of the best operator, linear operator to use. Now, there's a number of other kernels, right? Simple kernels that we can use to apply convolution. One of them is just the box kernel, stat, right? What is it doing? So you have one. How many is? What's the size of this kernel? That's 3 by 3, right? So the total size is 9. So what it's doing is just summing all of the pixels of this window in the image and dividing by the size, by the number of them. It's taking the average. It's taking just the average of pixels. Whereas this one is a Gaussian filter. You know, we all know what a Gaussian is, right? It's a bell-shaped function. This filter here represents a discrete version of the Gaussian. So it's like there's a peak here. It's a two-dimensional Gaussian. So I have a peak here, and then it's smoothly going down on both sides. Again, and the same thing here on the y, on the vertical dimension. There's a peak here. So, but this is just a discretization. Why do we use discretized Gaussian? Well, we can't apply a non-discretized version on a matrix, right? An image is just a matrix. So whatever we are doing is just simple discretization. All the methods that we're going to be using. We're going to read in papers, of course, they derive things using calculus and all sorts of functional methods. But in the end, once we are going to develop your algorithm, the only thing you have is a matrix. So you have to translate everything that you developed on a matrix, on a number of matrix operations. Good. So let's see the effects of box kernel. This is the effect. Let's see. This is the original image. And this is the effect of applying a box kernel of size 3 by 3. I can't see it much blurred, but you should get a little like blurred edges. Or if you look here, then you may see it kind of blurred. Or if you look this region here, you can see that it's not as defined as this. But it becomes very clear once you have a kernel of 11 by 11. Such as this one, applied to this one. This image is definitely is smoother than the original image. And a kernel of 21 by 21, it's the results in this region. So you can see that if you interpret this kind of pattern here as noise in the image, right? As noise in the image, you see that blurring, you got rid of some of this noise. Of course, you got rid of some information as well, right? It's some of the definition. I cannot see sharp edges anymore. It depends on what you want to do with your image. You can read on the book, then that's a good read. That why a blurring box filter works to get rid of noise. Box filter is just the average of your pixels in the windows. in your window. That's because the average is the value that minimizes the square error. Hey, we've seen that. We've seen that in statistics, right? We've seen that in statistics. So you are minimizing the error. So by minimizing the error, you're getting rid of some of the noise. That's nice, isn't it? But it minimizes the square error. Well, you know that there are other sorts of errors, and we're going to see in a minute another one. So this is a more complex Gaussian filter. You know that the Gaussian is just this function here. So you can have giant Gaussians, right? So it's an infinite function. So we go there and it goes into infinite on both sides. So where do we stop the Gaussian? Why don't we get a very large kernel? Would that make our filtering better? No, because we only by the 3 sigma rule, we see that values of a Gaussian function at a distance larger than 3 sigma can be ignored. So why is that? Because from basic statistics, and you can read more, this Wikipedia page is quite well written. If you want to learn more, of course, or you get a book on basic statistics, you see that if you get 3 sigma, you are actually representing in the Gaussian 99.7% of all of your data. So you don't need to pick up a larger Gaussian. You just need to pick up a Gaussian that's 3 standard deviations away from the mean value. All right? Okay, good. Yeah, so this is all what I said. That's why we don't need a very large Gaussian. We only need something that has 3 standard deviations away, and you're still discretizing it, so you can have an even smaller representation of your Gaussian with causing the same effect with a larger. Now, another advantage of using convolution is that the mean values of 2 convolutional Gaussian kernels, I obtain the mean values by just summing the mean values. The convolution, again, the convolution of an image of a matrix using 2 Gaussian kernels is the same as applying a single convolution summing up the mean values of the kernels. So filtering can be done in multiple stages with various kernels per stage. So if the kernels are Gaussians, it's possible to compute the standard deviation of the composite kernel. So you don't need to keep applying one kernel after the other, after the other, after the other. You just sum the mean values of all the kernels, and you can get the standard deviations, which is just the square root of the standard deviations to the power of 2, the sum of squares of the standard deviations, and you don't need to perform convolution on all individual kernels. You just need to apply convolution into one Gaussian kernel. That's nice, isn't it? So applying a low-pass filtering with a Gaussian kernel, we get this smoothing effect. So this is the original image. This is the original image. Gaussian kernel with 21 by 21. You get that. So you see the effect here. If you compare with the other one, where is that? With the other one, we have a much with the 21. Let's get look at the 21 by 21 with this image here. So this is we got rid of the noise, but we also got rid of sharp edges. By looking at the effect of the Gaussian smoothing with 21, we got rid of the noise, but somehow we kept some information of the sharp edges. Not all, but it's better than a box filter in this sense. Now, if you get a Gaussian filter, a Gaussian kernel of size 43 by 43, can compare with a kernel of 85 by 85, considerably larger. This is the result of a Gaussian kernel of size 43 by 43, and this is the result of a Gaussian filter of 85 by 85. Subtract one from another, and the difference is nothing. This is statistics proved, right? It's nothing, so you don't need to care about larger Gaussians. This is what I've just said, comparing a box kernel with a Gaussian kernel. This is the original image. Applying a box kernel, you see that that the signal is in the end is this kind of a trapezoidal, and kind of it's again, it depends on what you want. You don't see too much of an edge here, whereas if you have a smoothing function using a Gaussian, you have a much nicer result. Much well, a Gaussian smooths everything in a nicer way, in a very natural way. Okay, the effects of padding, just to close this part of the lecture. When zero padding fills up with zeros, the filtered results will have the filtered results using a convolution filter will have thick borders. You can use a mirror or symmetric padding, where the values outside the boundary are obtained by mirror reflecting the image across its border. It's more applicable when areas near the border contain details, or you can replicate padding. The values outside the boundary are set equal to the nearest image border value. More applicable when the areas near the border are constant. And this is the effect of zero padding. You see that you have added this dark boundary that's not part of the image. So you are inserting an artifact. The mirror padding is a much better effect, and the replicate padding almost the same effect as we get here. And we can use the low-pass filtering. One of the applications of the low-pass filtering is that, well, you know, if you want to extract the region of this galaxy, I think it's a star agglomerate. It's Hickson compact group. It's easier to just blur, because then I have a well-defined region here that if I want to segment. Now I only need to apply thresholding, that stuff that we've seen a couple of lectures ago, to get the region, exactly the region where this agglomerate is. And if I want to then go back, I can just select the pixels inside of this region from the original image to get the main body of the agglomerate. That's what thresholding with low pass filter is. That's one of the applications. The other application is shading correction. Now you have this one image, original image with some sort of defect. So you see that this part here is darker than the other part. Right? This is a defect on the imaging system. Then you can estimate the shading patterns. Given that, and then I get a better image, which is this resulting by dividing this this shading pattern with that. Right? And how do we get this? This figure, this pattern is just the result of low-pass filtering with a low-pass filtering the original image with a very large Gaussian kernel. Okay, finally, there is the final filter that I'm going to talk today with you is the nonlinear spatial filters. One of them is based on ordering or ranking the pixels in a region. That's the so-called median filter, where we're going to be replacing the value at the center pixel, the center of the neighborhood, with the value determined by ranking. What does it mean? So we're going to replace the center pixel value by the median value of the neighborhood. What you do is that you get your pixels in your neighborhood in the image. You order them from the smallest to the largest and pick the middle one. Then you get this middle value of pixels and substitute the pixel at the middle of your window of your neighborhood with the middle value or the median. The effect is that we are this is used to get rid of this kind of noise with salt and pepper when you see little particles of white and little particles of black, because these are like outliers, right? So a median filter is used to get rid of outliers, because the outliers will never lie in the middle of a sequence of values. The outliers will either be very too low or too high. This is the salt and pepper noise, an image with salt and pepper noise. So you see that there are particles of black particles and white particles always spread out together. If I apply a noise reduction by a Gaussian low-pass filter, I end up with this result here. You see, well, it's kind of good, but I lost details, so I don't see. If you look at these small details on the Gaussian, the resulting of a Gaussian convolution, they are not well precise. But if I apply the median filter, I get this very nice image. It's a very nice image, right? All the information seems to be there. Why does it work? It works because the median is the values. The median represents the values that minimize the absolute error, and not the squared error. It's the absolute error. By using the median, we do not create any new value as done in the mean. When you play the mean, you are creating a value that's not in the image. Where the median, you just pick up one of the values that are actual, one of the intensity values in the image. Right. Now, well, I lied. There is one more method that I want to talk about. This is a very new method called non-local means denoising. What it does, we've seen methods that pick up the average of a neighborhood, right? Or the mean of a neighborhood. But of a single neighborhood, right? Where is that? Let's pick up any image here. So we're always getting the neighborhood here, averaging out within this neighborhood, or getting the median and picking up the middle. And the same thing for the other neighborhood, and for the other neighborhood, and for the other neighborhood, independently of the statistics of the image. Now, with the non-local means denoising, I do the same thing, but I use regions throughout the image that are similar. So I pick up regions with a similar pixel intensity and apply the statistics on all of them to substitute one of the pixels. Right? This is a kind of nice, relatively new method that was published in 2008, and I'll show you a demo of it. Okay, so this is a nice site. Another one that I suggest you to see. That's it has a number of papers and a number of demos for these papers. And this is a demo of the method that we just talked about. That's the non-local means denoising. Now you can play with it. You can input your own image here. Let's pick up just one image from the site. This is the original image. Now we can add some noise, some salt and pepper noise, and apply the method non-local means denoising, and the result will be, whoops, this is the result. It's nice, isn't it? Noisy image, denoise image, compare with the original image. You see that there is difference. So the difference is just that. So you can subtract one from another and see what kind of, these are artifacts, right? There is no free lunch. If your method is very good, it means that you are applying some changes in the image. Okay, so I'll see you soon for the final part of this lecture, which is also very good. We're going to learn how to play with derivatives. So learn your convolutions before getting into the derivatives, because what we're going to do in this lecture, in this final part of this lecture, is we're going to develop kernels based on the derivatives of the image.